One last example. Let's imagine going from this alkene to this alkyne. And we have 1, 2, 3, 4 carbons here. And 1, 2, 3, 4 carbons here. So it looks like this is a new carbon-carbon bond. This ethyl group, this CH3CH2, is still a CH3CH2, so I know I should kind of number it that way, but my pi bond is gone. That's interesting. And I need to form this bond. So let's think about how to form that bond. Let's do our retrosynthesis, asking what starting materials I could have. And what I need to consider is if I want these two carbons to come together and form a bond, that means one of them started out as a nucleophile, one of them started out as an electrophile. So who's who? Which is which? Who would be the good nucleophile in this case? It's got to be the carbon that's part of the triple bond. So this guy was my nucleophile, which means this guy must have been my electrophile. Must have been an electrophile for it to be attracted to the nucleophile. And so what does this 2-carbon nucleophile look like? It's a C- with a CH, so it's the acetylide anion. That's a good nucleophile. And who is my electrophile? We have 4 carbons with a leaving group attached. So remember, we still have 1, 2, 3, 4. Careful with your line drawings. It's easy to lose a carbon at this point, so don't hesitate to number your carbons and number them throughout so that you don't miss any carbons. If I had this alkyl halide, bromide, chloride, iodide, and I reacted it with this nucleophile, would I get this product? Sure, I'd expect an SN2, and so that looks great. So the question is then, how do I go from my alkene to this bromide? I need this bromide in order to do my synthesis, I'm starting with an alkene. So it looks like the double bond's gone. I've added a bromine. What else? There's also a hydrogen here that was new. So how about if I just add HBr? I can take an alkene and I can add HBr across the pi bond, break the pi bond, add an H and a Br. Would that give this product? What's the problem with just adding HBr? What's the regiochemistry you expect when you add an HBr? Hydrogen goes to the carbon with more hydrogens. That's the end carbon in this case. So that would give the wrong product. So how do we get to anti-Markovnikov regiochemistry? Well, there's a few things that we need to, a few options we've had. We've seen one case where we did hydroboration oxidation, so we could first make the alcohol and then convert it to the Br. But we've actually seen a reaction with Br. It's a good thing we picked Br as our leaving group, because we've seen a reaction with HBr that added anti-Markovnikov. And that was, instead of using a mechanism with involving HBr as an acid, we threw in some peroxides. When we add in peroxides, we get a radical mechanism. And we get anti-Markovnikov regiochemistry. So that would be a way of adding the hydrogen to the middle carbon and the bromine to the end carbon. And then once we have this, we can add in our sodium acetylide, okay, which you can assume that you can just get commercially, or you could show how you make that. It depends on the instructions for the particular assignment. You could do that as well. Okay, one thing that I wanted to point out is that I forgot to mention is that this nucleophile is a very strong nucleophile. It's also a strong base. Okay, so FYI, if we tried to react this with a secondary leaving group, or definitely something with a tertiary leaving group, then we're going to get E2 elimination instead. So for example, if I took cyclopentyl bromide and I tried to do reaction with this to do an SN2, remember SN2 is very sensitive to sterics, and as soon as we have any kind of steric hindrance like this, rather than do the SN2, it's going to give E2 as the major product. So for this alkylation process that we're talking about, we need to have an unhindered electrophile, something like a methyl halide, like methyl iodide we just saw, or a primary alkyl halide. Primary RX is a good SN2. Okay, if you don't want to use this peroxide, this radical mechanism, or you don't recall that, the other anti-Markovnikov mechanism that we should know is the hydroboration oxidation. So in other words, we can add water across the pi bond in anti-Markovnikov regiochemistry. So that was BH3THF, hydroboration, oxidation, H2O2 and base. A few more reagents to remember if you choose to go this route, but that'll work just as well. Okay, and now we also have an extra step because we can't just add in the acetylide. We don't have a leaving group. So what we would need to do is we need to convert this to a leaving group. How do we make an OH a good leaving group? Several options. We can make it the halide by using something like PBr3. Or we could make it the tosylate by using tosyl chloride. Okay, either of those would be good, and if then we could react that with the sodium acetylide. We can get an SN2 with our nice primary leaving group, and that would be another route to it. This step is a little longer because it requires conversion of the OH into something bearing a good leaving group. So this first method would be a little better because it's more succinct and a shorter synthesis. That finishes it up for alkynes, and I hope to see you again soon at Educator.com. Thank you.